So I suppose if we had to name this section, we would talk about how this is organic bonding, covalent bonding with carbon and similar elements in organic chemistry. Let's look at hydrogen. We'll start out with that. Hydrogen, you know, when you draw a Lewis dot structure for that, hydrogen has one valence electron. Now, if you don't remember what a valence electron is, you should probably look that up. Hydrogen has one valence electron, and it wants to have two because hydrogen's electron configuration is 1s1 whenever it's a neutral atom. Everybody wants to be a noble gas, and so the next closest noble gas is actually helium, which has a 1s2 configuration. So hydrogen wants another electron. In nature, we find hydrogen as a diatomic molecule. That's how elemental hydrogen shows up. You remember from general chemistry, you always wrote it as H2 when you're talking about elemental hydrogen. Well, here's why. So hydrogen has its one electron in its Lewis dot structure. That's the valence electron. It comes into contact with another hydrogen atom, which has a single electron also, and these two form a pair of electrons, and they now share this pair of electrons, and that's the covalent bond here. Another way that this is drawn often is going to be a straight line in between the two, because we see those as a bond in between those two atoms. So now, instead of having an electron configuration of 1s1, you'll see that they're sharing an electron, so they both have the configuration of 1s2. Well, guess what? That's helium's electron configuration. Everybody wants to have a full outer shell. So hydrogen, as a result of having one electron and only two possible electrons going into that energy level, it can only form one bond. If you ever see a double bonded hydrogen, it's wrong. It just isn't going to happen that way, because a double bond would be sharing 4 electrons between the two hydrogens, or 4 electrons between the hydrogen and whatever element that it's bonded to. So that's hydrogen's special nature of that. Okay, let's go across and look at. See, I got a text message now. I'm distracted. All right, so now let's go across and let's look at carbon. This is the one that we talk about the most. Now, carbon, when we draw the Lewis dot structure of that, it's going to have 4 equally spaced electrons around it. Why is that? Well, here's why. Because when we draw the electron diagram for this, we'll get the first energy level, the 1s, we have 2 electrons. And then we go up to the 2s, and then you would say, well, carbon has 4 total, so you would want to draw it out like this, and you would say, okay, so 2s, there's 2 there, and then we have 1, 1, and then none in the third p orbital. Well, that's not actually what happens. What happens in reality is we have what's called a hybridization of carbon. And these energy levels are so close in energy that whenever this electron can move over to this p orbital, and they all balance out. So this would actually be drawn more like here's our carbon, there's the first energy level, and then the second energy level, we would have 4 equal in energy orbitals. Let me see. Let me move this up. Let me move this out of the way. It's a little close. Let's move it up some. All right, so those are 4 equal energy levels, and then the electrons actually fill with a 1, 1, 1, and 1 electron. This is the valence shell. That's the valence orbitals. That's the second energy level for carbon. So that's why carbon is drawn like that. As a result, carbon, when it comes in contact with hydrogen, carbon has an electron here, hydrogen has its electron here. They will share that pair. So you may see it drawn as 2 electrons like that, or more conveniently, we do draw that as H and then C. Carbon, since it has 1, 2, 3, 4 possible bonding points, can make exactly 4 bonds with hydrogen. I ran off the bottom of my page there, but you should see, and that is methane gas. Or as they say across the pond, methane. Now that's special bonding with carbon. So let's look at this. Common elements that you'll see in organic chemistry. We have hydrogen, we have carbon, we have oxygen, we will have fluorine. We actually see chlorine probably more often. So how does this pan out for us? Well, hydrogen, of course, Lewis dot structure has 1 electron on it. Carbon has a Lewis dot structure which has 1, 2, 3, 4. We only draw the valence electrons. Oxygen has a Lewis dot structure which is oxygen in the middle. We have a pair, another pair. Oh, you know what? I forgot nitrogen. I'll put that one in. I knew I was forgetting something. Fluorine is a halogen. They all have 7. They have special bonding 3, 4, 5, 6, 7 because they can only make one bond. Also, fluorine can. Chlorine can make more. There's complications that take place there. We can talk about that later. It's not important for what we're doing now. And then nitrogen, which I skipped, which should have been right here, is nitrogen, which then has a pair of electrons and then 3 lones. So when you look at these Lewis dot structures for the elements, you'll see that hydrogen has 1 lone electron. Carbon has 4, which means it can make 4 bonds. Oxygen has 2 solo electrons, so it can have 2 bonds. All of your halogens, fluorine, chlorine, bromine, iodine, etc., they have 1 single electron, so they can make 1 bond. And then nitrogen has 1, 2, 3, and it makes 3 bonds. Now, to reiterate this and try to drive this point home, if you remember your diatomic elements, hydrogen is diatomic. All right, hydrogen, and then we move across and we'll see that the next diatomic is nitrogen, and then oxygen, and then fluorine, and then chlorine, and then bromine, and then iodine. 1, 2, 3, 4, 5, 6, 7. Yep, 7 of them. 7 diatomic elements. All of those make those are found in the those are diatomic elements. They're molecules in nature. Hydrogen, we just showed a moment ago, when it's in nature, it's H2, and it's bonded to hydrogen like that. Nitrogen, remember here, we said it can form 3 bonds. When nitrogen bonds with itself, it has 3 bonds. And then there will be a lone pair of electrons on each nitrogen. Oxygen bonds to itself. It has a double bond. Remember, oxygen has 2 bonds. And then it will have 2 lone pairs on each atom. Fluorine bonds to itself with a single bond. And as a result from that, it will have 3 lone pairs. We get more into this. Chlorine, bromine, and iodine all do the same thing as fluorine. So you see all these, they all bind to themselves similarly. So I can just draw that again. Now, we always need to make sure that we recognize when there are lone pairs present. So we need to be familiar with these elements because these lone pairs are important. If you run across a molecule that I may draw out later, and I'm going to have carbon double bonded to an oxygen like that, and then I have a hydrogen over here, just like that, I'm not always going to draw those lone pairs of electrons, but you need to remember that there's going to be lone pairs of electrons on that oxygen. You look at the hydrogen. Hydrogen needs 8 electrons, and so if we're looking at hydrogen here, carbon needs 8 electrons. Hydrogen only needs 2. Carbon needs 8 electrons, so you see we get 2 from there, 2 from there, 2 from there, and 2 from there. So there's your 8 electrons on carbon. So carbon can make double bonds. It can make triple bonds, but nobody makes quadruple bonds. It's just a physical impossibility. When I get my model kit in, I can illustrate that using the model kit because it's really easy to see when you look at it in 3 dimensions.